Our next speaker is Edgard Pimentel from the Federal University of São Carlos, Brazil, and the Federal University of Ceará. And he's going to be talking about elliptic mean-field games.
Okay, so thank you, Professor Manuel, and thanks for the opportunity to talk about my work to this audience. It's important also to express my gratitude to this organizing committee for the efforts to putting together this scientific program for these 2 weeks, and for the thematic program. It's a joy for me to be part of this and to be able to attend it. So thank you for that. So today I'm talking about elliptic mean-field games, and this is based on joint work with Vardan Voskanian. There's currently called Saudi Arabia, right? So the plan for today is to start presenting you the problem, and the problem we're investigating is precisely that, right? We have a system of nonlinear partial differential equations. The first equation is a Hamilton-Jacobi equation, and the second one is a Fokker-Planck equation, right? And these are coupled through 2 distinct structures of the system, right? So the first structure is this G of M, and this map is supposed to encode the dependence of the Hamilton-Jacobi equation on the density M. And in addition, we have here this term dph, right? There is the derivative of h with respect to the second coordinate evaluated along x and d of u, the gradient of u. And then the system couples these equations through the mean-field coupling and also the optimal control of the optimal control problem encoded by this Hamilton-Jacobi equation, right? So in addition to that, H will be our Hamiltonian, and H bar is called the effective Hamiltonian of the problem, right? Okay, so here the unknowns are the function u, the function m, and the effective Hamiltonian H bar, right? H bar is a scalar, u and m will be functions. We'll be looking for functions in appropriate function space, right? So what's our goal? Our goal here is to establish the existence of smooth solutions for this system. So we're looking for u and m, there is infinity, and some h in R, right? And the plan to do that is to investigate separately the regularity of solutions, a priori regularity for this equation in terms of solutions to this equation and vice versa, right? Okay. So with that said, let me tell you what's been around regarding this problem. So the first paper addressing the system is by Jean-Michel Azri and Pierre Lyons, in which they proved well-posedness of solutions in the class of weak solutions, right? And in another paper in 2007. So these papers are well known by now as the papers introducing the mean-field games theory, where actually there are several results, several important results here, and one of them is the well-posedness in the class of weak solutions for system 1, right? So a few years later, Diogo Gomes, Stefania Patrizzi, and Vardan Voskanian established the existence of smooth solutions for the system 1 under the hypothesis that the Hamiltonian is quadratic and under periodic boundary conditions, right? So it's the same thing we are considering in terms of the special variable with the periodic boundary conditions, okay? So this result appeared in 2014, but we were of course aware of that before. And after this paper, then I concluded my PhD under the direction of Diogo Gomes in Lisbon. And then something crossed my mind, and we were talking, Vardan Voskanian and myself, and we decided to do what? In my doctoral work, we developed some classes of estimates for parabolic mean-field games problems, mean-field game systems, right? And the idea there was to explore some sort of polynomial estimates for the Fokker-Planck equation, okay? And what Vardan and I were trying to do was to import this idea. Of course, it's not about replicating the techniques, but to explore the analogy between what would be polynomial estimates for the elliptic setting, right? And then try to see what would happen. But notice that this approach concerns only the Fokker-Planck equation, right? So by this year, Marco Serran from Padova published a paper in Journal Mathématique Pure et Appliquée, in which he investigates mean field games, stationary mean field games, but then propose a very innovative and very original approach to investigate the regularity of the Hamilton-Jacobi equation, right? And this is done through the integral burst time method. So that's exactly what we were after somehow, because our idea was to import techniques from the time-dependent problem to investigate the regularity of the Fokker-Planck equation. But then, and then it would be perhaps something, but actually, if we build upon Marco Serran methods for the Hamilton-Jacobi equation, then what we can do is actually much more interesting. Okay. So in this spirit of this short story, let me tell you what our main result is, right? So this is by myself and Voskanian, Vardan Voskanian. So we assume the Hamiltonian satisfies a growth condition of this form, right? So in infinity, it's just a constant plus a constant, p raised to some gamma, and gamma is above 1, so it's always superlinear. And then we make assumptions on the mean field coupling, right? So mean field coupling can be of two types. So first, this is a power-like nonlinearity, and the exponent satisfies this kind of constraint involving the growth of the Hamiltonian and the dimension. Or g of m is the logarithm of m, right? And in this case, there is a constraint as well, but it hits the growth of the Hamiltonian instead of any other parameter. Okay, so this result, if we assume this growth condition and this hypothesis on G, then what we've managed to prove is the existence of a unique smooth solution to the mean field game system, right? And well, let me tell you why this result is interesting. Well, this result is interesting because it's the first time that we can accommodate general Hamiltonians of this kind, right? In the setting of smooth solutions, right? On the other hand, for higher dimensions above 6, this constraint in alpha is the best you can get, right? Because if you allow D to be only above 2, then Diogo's result for the case 2 where Marco Serran results better than that. But then for D, for higher dimensions, then what we do is actually better. And this condition and the growth of the Hamiltonian also is better than the one obtained by Diogo, Stefania, and Vardan in their paper. But when we compare with the results in Marco Serran's, in Marco Serran's paper, there is an assumption on G that G must be bounded from below, right? Which automatically rules out this kind of nonlinearity. So this result somehow improves what's been done so far, right? So once we know what kind of result we've managed to establish, then let me show you more or less what's the strategy of the proof. So in this business, the kind of strategy we are used to is to obtain a priori estimates, right? And then once we do that, we hope to have enough to establish existence of weak solutions, smooth solutions, or whatever. But for these problems, there is one initial level of a priori estimates that are pretty much for free. I mean, if you integrate the equation, then you automatically controls u in w1 delta for small values of delta or this kind of things. But then there is some way that you have to do something, right? That you have to do something that will actually gives you some level of regularity that gives you C infinity, right? So the hard part of the thing is this, okay? So what do we want to get here? Here what we want to get typically will be something like estimate the gradient of u in some LP space by constant g in LQ, perhaps raised to some power, and conversely g in LQ, constant du in some LP raised to another power, right? If you're fortunate enough, then what you have would be something like this. And then elementary inequalities save the day, and you have, for instance, du uniformly bounded, right? So once you have that, then you are in this critical way to see infinite regularity. So let me show you some of the estimates that allow us to do that. Okay, so following from the integral Bernstein method, what we have is an estimate of this type, right? So here we can control du in LP in terms of constant g in LRP, but then we can send p to infinity because of this condition for RP, and also because these constants, they don't depend on p, right? So this is the typical estimate we need for solutions of the Hamilton-Jacobi equation. Also, we need regularity for the density m. So in one of the cases is this one, we have power-like nonlinearities. The typical estimate we'll have will be m in LR in terms of a constant, this quantity raised to some power. Here, 2 star is the Sobolev standard exponent, right? And we can also obtain this in the L infinity setting. In the case of logarithmic nonlinearities, thing goes more or less the same. And here it appears the growth condition of the Hamiltonian, right? So you see the constraint we have on the growth of the Hamiltonian, for instance, is entailed by this kind of constraint, right? We must have exponents that are below 1 to apply, I don't know, Young inequalities or this kind of thing. And then it imposes conditions on these guys, right? So this is the problem. This is the result. These are the basic steps toward that. And I'm grateful for your attention.